Off the western edge of North America lies one of the most deceptively dangerous tectonic systems on Earth. It is small compared to giants like the Pacific or Eurasian plates, and most people have never heard of it. Yet its behavior has the potential to reshape coastlines, devastate cities, and alter ecosystems across an entire continent. This is the Juan de Fuca Plate, a thin slab of oceanic crust caught between much larger plates and steadily being pushed beneath North America. Unlike fast-moving surface processes, this interaction unfolds slowly, centimeters per year, invisible to everyday life. But over decades and centuries, that slow motion matters. Stress accumulates along the plate boundary, deep earthquakes occur within the slab, and heat and fluids released at depth help fuel volcanic systems hundreds of kilometers away. The result is a region shaped by multiple interconnected hazards rather than a single threat. What makes the Juan de Fuca Plate especially important is the contrast between how quiet it often seems and what it is capable of producing. Geological records show that it has generated some of the largest earthquakes on the continent. Understanding how this plate formed, how it moves, and how it interacts with North America is key to understanding the risks facing the Pacific Northwest today. Before we dive in, don't forget to click on that subscribe button and like this video, as it's the best way to support this channel. The Juan de Fuca Plate is the remnant of a much larger tectonic plate known as the Farallon Plate, which once occupied most of the eastern Pacific Ocean. Over tens of millions of years, the Farallon Plate was consumed beneath North America, fragmenting into smaller plates as spreading centers migrated and reorganized. What remains today are several microplates, including the Juan de Fuca Plate, the Gorda Plate to the south, and the Explorer Plate to the north. This plate is formed at the Juan de Fuca Ridge, a mid-ocean spreading center where magma rises from the mantle and creates new oceanic crust. As new crust forms, it is pushed eastward toward North America. The plate is young, relatively warm, and buoyant compared to older oceanic plates, characteristics that strongly influence how it subducts and how stress accumulates along the margin. Despite its modest size, the Juan de Fuca Plate plays a central role in shaping the geology of the Pacific Northwest. Its existence explains the region's volcanoes, earthquakes, coastal uplift, and the hidden seismic threat lurking offshore. The Juan de Fuca Plate lies offshore of Northern California, Oregon, Washington, and British Columbia, occupying the oceanic realm just west of the continent. Along its eastern edge, it meets North America at the Cascadia Subduction Zone, a roughly 1,000-kilometer-long plate boundary extending from Northern California to Vancouver Island. Subduction is the key process. The Juan de Fuca Plate is pushed beneath the North American plate as the plates converge. The convergence rate is often summarized as roughly about 4 centimeters per year along much of the margin, slow in everyday human terms, but geologically fast enough to load enormous energy into the fault system. The most feared Juan de Fuca related hazard is the Cascadia megathrust, the boundary where the plate dives under North America. In locked segments, the plates are effectively welded together by friction. When the fault eventually breaks, it will produce a megathrust earthquake that can last minutes and rupture hundreds of kilometers in one event. The Cascadia boundary is capable of magnitude 9 class earthquakes. The U.S. Geological Survey notes that the National Seismic Hazard Model uses an approximate 500-year recurrence interval for full margin magnitude 9 Cascadia ruptures, based on multiple lines of evidence such as coastal subsidence, tsunami deposits, and offshore sediment records. A time-independent recurrence model implies roughly a 10% chance of another magnitude 9 event in the next 50 years. What makes this especially dangerous is the combination of earthquake size and proximity. That means severe shaking, long duration, broad regional impacts, and a real chance of a locally generated tsunami, often with little warning time for nearby shorelines. A Cascadia megathrust earthquake is dangerous partly because it can generate a tsunami through vertical motion of the seafloor. When a large portion of the plate boundary ruptures, it can abruptly lift or drop the ocean bottom, displacing enormous volumes of water. In near-field coastal zones, the first wave can arrive quickly, and the most damaging wave is not always the first. The 1700 event demonstrated that Cascadia can send tsunami energy across the Pacific. For the Pacific Northwest coast itself, the major hazard is the local tsunami, where evacuation time may be measured in minutes rather than hours. This is why coastal communities treat earthquake shaking as the natural warning. If you feel long or strong shaking near the coast, you move to high ground immediately. Tsunami risk also depends on local coastal shape. Bays, river mouths, and inlets can amplify wave effects, and low-lying estuaries can be struck by both wave inundation and subsequent flood dynamics. The tsunami is the dramatic headline, but the less dramatic, longer-lasting consequences may be just as disruptive. Even without a megathrust rupture, the Juan de Fuca Plate produces dangerous earthquakes from within its own descending slab. These are called intraslab earthquakes and can occur tens of kilometers deep beneath the plate and beyond. A well-known example is the 2001 February 28th Nisqually earthquake, which occurred about 52 kilometers deep on a fault within the subducting Juan de Fuca Plate. Deep earthquakes can be especially deceptive. Because they occur at depth, they may not produce the extreme surface rupture effects of shallow crustal quakes, but they can still generate strong shaking across wide regions, affecting multiple cities at once. Their depth also means the waves spread out differently, sometimes producing a broader footprint of moderate to strong shaking and stressing older structures, bridges, and critical infrastructure. Intraslab quakes are part of the Juan de Fuca danger profile because they do not require the megathrust to break. They are a reminder that even during quiet decades at the subduction interface, the slab itself can still produce damaging events. The Juan de Fuca Plate does not merely create an earthquake and tsunami problem. The plate is also the driving force behind the Cascade Volcanic Arc, a chain of volcanoes that stretches from Northern California through Oregon and Washington into British Columbia. As the plate descends beneath the North American plate, it carries water-rich minerals and sediments deep into the earth. With increasing pressure and temperature, this trapped water is released into the overlying mantle. The presence of water lowers the melting point of mantle rocks, allowing partial melting to occur even without extreme heat. This newly generated magma is buoyant, so it slowly rises through the crust, feeding volcanic systems far inland from the coast. Over time, repeated pulses of magma build the chain of volcanoes known as the Cascade Range. The depth and angle of the Juan de Fuca Plate control where this melting occurs, which is why the volcanoes form in a narrow belt rather than randomly across the region. As long as subduction continues, this process remains active, sustaining volcanism over geologic timescales. Mount Rainier is a prime example of a Cascadia-related volcanic hazard with direct downstream consequences. USGS notes that Rainier is particularly susceptible to lahars because of its abundant snow and ice, and because some slopes have been weakened by hydrothermal alteration, conditions that can produce large flows capable of destroying or burying structures in their paths. Importantly, lahars can be triggered not only by eruptions, but also by landslides, and earthquakes are among the plausible triggers in a region where strong shaking is part of the hazard landscape. The Juan de Fuca Plate, then, does not create a single impending danger. It creates an interconnected hazard web where a subduction earthquake can damage infrastructure directly and also cascade into secondary disasters. The future behavior of the Juan de Fuca Plate will continue to be defined by slow but persistent subduction beneath North America. While the exact timing of major earthquakes or volcanic events cannot be predicted, the physical processes driving them are ongoing and well understood. The plate continues to converge with the continent, steadily accumulating strain along the Cascadia subduction zone and maintaining conditions that allow magma generation beneath the Cascade Volcanic Arc. This means that seismic and volcanic hazards in the Pacific Northwest are not temporary anomalies, but long-term features of the region's geology. Advances in monitoring are improving how scientists track these risks Dense seismic networks, continuous GPS measurements, and offshore instruments are providing clearer images of where the plate boundary is locked, where it is slowly slipping, and how stress is distributed at depth. Over time, these data will refine hazard models and help distinguish between regions of higher and lower risk, even if precise forecasts remain impossible. From a societal perspective, the future outlook depends as much on preparedness as on geology. Continued investment in resilient infrastructure, updated building codes, and public education can significantly reduce losses when large events occur. The Juan de Fuca Plate will remain active for millions of years, but informed planning can determine how disruptive its future impacts will be.